To measure things, we need units. Here's a sentence. When my son was 7, he walked 3, and when he was 4, he could throw his baseball 8 and tell us that his school was 5 away. What the heck? What does that even mean? This is a sentence with measurements and no units. It doesn't make sense. It's like going to McDonald's and say, I want 5. They're like, well, do you want meal number 5 or do you want 5 of something? They don't know, right? Units are really, really important. I think what this is supposed to mean is when my son was 7 months old, he walked 3 steps, and when he was 4 years, he could throw his baseball 8 feet and tell us that his school was 5 blocks away. Okay, well that makes more sense now when we get some units in there. So units make a big difference, really important. There are 2 common unit systems, the English system and the metric system. Here in the United States, we do a lot of things in the English system. We're generally familiar with it, but it's a vastly inferior system, and we just hold on to it because we're stubborn Americans, and we don't want to change. Most of the rest of the world uses the metric system. The metric system, once you get used to it, makes so much more sense and is much easier to use. So we're going to use the metric system. Here's another example of why units matter. 1999, NASA lost a $94 million orbiter because 2 groups of engineers failed to communicate about the units that they used in their calculations. And so the orbiter descended too far into Mars's orbit, Mars's atmosphere, and burned up. Basically an inches versus centimeters problem. Some of the calculations were done with inches and some with centimeters, and they didn't communicate well. $94 million. And how many man hours shot? And like public embarrassment, right? So don't be NASA. Basic units of measurement. Okay, scientists use the International System of Units, or SI units. It is based on the metric system. It is not exactly the same as the metric system. For our purposes, the differences do not matter. There are very slight differences in terms of what is considered a base unit, but I don't care about that at all. So your book's going to talk about the SI system. I think metric system is easier to say, and it means essentially the same thing. These are the base units in the SI system. Length is measured in meters, mass in kilograms, time in seconds, that one's familiar, and temperature in Kelvin. We're not going to talk about temperature until chapter 3. So base units. The metric system has a base unit, and then to make the unit bigger or smaller, we use prefixes instead of just using different units. So if we think about length, measuring length or distance in the English system, if I wanted to measure how long my calculator was, what unit would I use? Inches, probably. I wouldn't use yards or miles, right? It'd be silly to measure a calculator in miles because the number would be ridiculously small. I live in Reedley. I drive to Fresno to teach. Would I measure the distance from Reedley to Fresno in inches? No. I wouldn't even do it in feet or yards. I'd do it in miles, right? It's convenient to use a unit that is similar in size to what you're measuring. That's why we have all these different units, because we need units of different sizes. So in the metric system, there's a base unit, and then we use multiples of 10 to make it bigger or smaller. So for length, we use the meter. This is how they define the meter. There's an illustration of it. I'm not going to test you on that. It's kind of interesting. What I want you to know that is a meter is slightly longer than a yard. So here we have, this is not a yardstick. This is a meter stick. But just looking at it, it'd be hard to tell. So a meter is the whole length, and a yard is up to here. So a yard and a meter, very similar in size. If you have a concept of how long a meter is and you're doing a problem, you can look at the answer and see if it's reasonable or not. So, if I calculated the length of this bench and I came up with 4,000 meters, would that be reasonable? No. Something went wrong in the calculation, right? I should go back and look at what I did. For a mass, the base unit in the SI system is the kilogram. Here is a picture of the official kilogram. It's a block of metal in France, kept very securely there. A kilogram is slightly bigger than 2 pounds. So, the mass of a person. Could a person weigh 500 kilograms? Well, that would be over 1,000 pounds. Probably not, right? But could a person weigh 50 kilograms? Yeah, that'd be a little over 100 pounds. That's reasonable. So just have an idea of how big these things are. What the unit we're going to use a lot is the gram, which is smaller, but we'll get into that. So kilogram is a measure of mass. Mass and weight are similar, but there is an intrinsic difference. Mass measures the quantity of matter in an object, and weight measures the gravitational pull on that object. So if you weigh, let's see what would make it easy, 1/6. If you weighed 180 pounds on Earth and you went to the moon, where the gravitational pull is 1/6 that of the Earth, and you brought a scale with you, you'd weigh 30 pounds on the moon. Does that mean you lost much of your body in the course of traveling to the moon? No, you're still the same person, you're still the same size, your genes still are going to be tight, right? It's not that you lost weight, it's the gravitational force is smaller on the moon. So mass, your mass doesn't change. Mass is how much matter, how much atoms, how many molecules are in your body, that's staying the same. So weight depends on gravity, mass doesn't. Now, anybody planning to leave the Earth during the next 4 weeks? No? I didn't think so. So, as long as we're staying on the same planet, the differences are small, but I just want you to be aware of them. So the gram is another common unit of mass. It's much smaller. It's what we use more often in chemistry because we weigh smaller things. So a gram, a nickel is about 5 grams. So you think a nickel is 5 cents, it weighs about 5 grams. So that gives you an idea of how much a gram is. It's pretty small. For time, we're in luck because the unit is the same. It's a second. A second is defined as the duration of this many periods of radiation emitted from a particular transition in a cesium-133 atom. So that's how they would establish that. It's based on an atomic clock. I won't test you on that, but that's where it is. So to change the size of these base units, second, gram, and meter, we use prefixes. And the prefix multipliers are just powers of 10. So we choose a prefix multiplier that makes the unit a convenient size. So a meter is about a yard. It's about this long. So if I was measuring, the distance from the whiteboard to the back of the room, a meter would be a convenient unit, right? I could just go back and measure that. If I was measuring the distance between my home in Reedley and Fresno, a meter would not be useful. I'd want a larger unit. The unit I would probably choose would be kilometer. A kilometer is 1,000 meters, so it's much larger. It's more on the range of a mile. So the prefix kilo means 10 to the third, or 1,000. So 1 kilometer is equal to 10 to the third meters. You can also express that as 1,000 meters. So kilo is a prefix that makes the unit larger. So instead of having to remember there's 12 inches in a foot, and there's 3 feet in a yard, there's 5,280 feet in a mile, I can't remember the yard to mile one. All we have to do is learn these metric prefixes and what they mean, and we can do all the unit conversions in the metric system. It requires a little effort up front, learning the prefixes, but then it's all about factors of 10. So these are the metric prefix multipliers. There are others. These are the only ones that you will need to know. So tera has the symbol capital T. Giga is capital G. Mega is capital M. Kilo is lowercase k. Now, if you're at all into computers, you may recognize these. These are prefixes that are used in measuring storage capabilities for computers. It's now not uncommon to have a 1 terabyte hard drive, right? Terabyte means 10 to the 12 bytes. A byte is a unit of memory storage. A gigabyte is 10 to the 9th. So 1 terabyte is 1,000 times larger than a gigabyte. Megabyte, kilobyte. It's also helpful to see these capital symbols make the units larger. This kilo is an exception to that. Kilo does make it larger, but not as large. Deci is lowercase d, centi is c, milli is lowercase m. So we had capital M, that made it bigger. Lowercase m makes it smaller. So this is the multiplier 0.001, or 10 to the minus third. So big M makes it bigger, small m makes it smaller. Then we have micro. We have now used up both the capital and the lowercase m in the English alphabet, so then we're going to go to the Greek alphabet. And this funny looking backwards y is mu, which is lowercase Greek m. That means 10 to the minus 6. And we've got nano and pico and femto. So for the most part, these symbols are just the first letter of the prefix's name. What you need to memorize are these numbers here. You could memorize these, but I think that's a lot harder than memorizing the powers of 10. If you notice, most of these are multiples of 3. We've got 12, 9, 6, 3. Okay, those two are weird. Minus 3, minus 6, minus 9, minus 12, minus 15. So throughout this course, I'll be kind of giving you some hints. I'll say, okay, if you're an A student, like for this, if you're an A student, you should know all of those. Okay? We can't always do the best because we sometimes have other things going on in our lives, right? And so sometimes we have to put our effort where it's going to mean the most. And so I want to assist you in that. I know some of you are not going to have as much time as you would like to devote to chemistry during this 4-week session. So what if you can't take the time to memorize all of them? Well, you need to know what centi and milli and micro and kilo. Those are the 4 most important. If you don't know those, you're going to have a hard time passing a class. So that's the bare minimum. Okay, those are the bare minimum. You need to know those. I'd encourage you to try to learn them all. There's going to be several things, several subjects where there's stuff you need to memorize. This is one of them. Index cards. Okay? Pack of index cards at the dollar store. Write the prefix on one side and the symbol, and write the factor, 10 to the something on the other side. Carry them with you. You're waiting for class to start, flip through your note cards. You're waiting at the train because you got stopped by train, flip through the cards. Okay? You're waiting for the microwave to heat up your frozen burrito because that's all the time you have. Flip through your note cards. Okay? There's lots of little bits of time that you can use if you're motivated. Okay, which is the most convenient unit to express the dimensions of a poliovirus, which is about 2.8 times 10 to the minus 8 meters in diameter? Okay, this is an example of a word problem, right? Or we used to call them story problems, which I think makes them sound more fun. It's a story problem, right? There's people who love story problems and there's people who hate story problems. And it's just how your brain's wired. It doesn't have to do with your intelligence. But it does make some chemistry problems more difficult if your brain does not like story problems. So the poliovirus, that's just like put in there to make it interesting. We're just trying to take this number and figure out which of these units would be the most useful to express that. So we want a unit that's similar in size. So this is smaller than a meter, right? So we don't want to use a unit like megameter that is larger. So we could get rid of that one. So that one's out. That one's not going to be good. Well, now we've got these. These are all making it smaller. We've got milli, micro, and nano. A millimeter, milli means 10 to the minus 3. So this is 10 to the minus 3 meters. Micro means 10 to the minus 6. And nano is like the word 9. Nano is 10 to the minus 9. So a nanometer is 10 to the minus 9th meters, micro 10 to the minus 6. So this is 10 to the minus 8th meters. Which of these is that closest to? It's closest to this one. We'd like a unit that's a little smaller than what we're measuring so that we have nice numbers to deal with. So we would probably choose nanometers to express that. So the base units, time, mass, and length, and then we have derived units. Derived units are a combination of other units. So volume. Many volume units are derived units. So if you take a unit of length, such as a meter, and you cube it, you get a unit of volume. So if we think of geometry, and we've got a cube, and each side is 1 meter in length, the volume is the length times the width times the height. Right? So the volume equals the length, 1 meter, times the height, 1 meter, times the width, 1 meter, and that is 1 meter cubed. So meters cubed, centimeters cubed, inches cubed, those are units of volume, derived units of volume. Liter is also a unit of volume. Liter is not a derived unit. These are usually used for liquids, like you would use ounces or gallons, liters and milliliters. 1 liter is similar in size to a quart. Everybody should be familiar with how big 2 liters is, right? A 2-liter bottle of soda is 2 liters. So that gives you an idea of how big a liter is.